Hi, and welcome back to MacroLearning, the organic chemistry part. This is another question about alkanes. Are the following pairs of structures structural isomers, conformers, cis-trans isomers, or identical? Well, I'm showing only the first structure here, but we'll deal with the others later in this question, or later in this video, I'm sorry. But are these same compound, identical structures, or structural isomers, or conformers, or cis-trans isomers? Well, let's see. What we can see here is that both structures have the same connectivities of all the atoms, all the atoms, because once we draw them in regular structures and put the front carbon here on the left, what we get is this one for this, and for this other one it's again the front carbon on the left, still with CHCl2 with CH2 CH3. So both are the same structure, same compound with same configuration. Configuration meaning the order in which all the atoms are connected to one another. Okay, so they're just conformers, because if you look at this one and this one, the front group are the same. The front guys. If we keep the front guys fixed and rotate the back groups by, say, 120 degrees, then what you get is you get this. So any structure then can be obtained by rotating carbon-carbon single bond, such as if you rotate this back three groups by 120 degrees, any structure that can be obtained by doing that will be another conformation. You can't get another structure by doing that. You can't get another configuration by doing that. You won't change the structure or the order in which the atoms are connected. All you can get is another conformer. Okay, so there are different conformations of the same compound. So they are conformers to each other. Okay, so that's that. The next question, the next part. Okay, now this pair is a little different, because once you draw it into the regular structure, it will be like this. Again, if we put the front carbon on the left, put the other one on the right, it will be this for the left one, okay, and for the one on the right, it's gonna be, instead of two chlorines, it's got one methyl and one chlorine, and on the right there's a chlorine. So now it's pretty easy to see that they are just different compounds. They're structural isomers, different compounds, but the same formula, right? But different structures, different connectivities of all the atoms. Here we have two chlorines on the left for one thing, and here we have one here and one on the right. So they're structural isomers. No need to even consider the cis-trans things or conformations. They're just different structural isomers. That's all. Structural isomers. That's what you call structural isomers. Alright, next part. Okay, so this pair of structures, I think, to me, they look like cis-trans isomers. Cis-trans isomers, because if you look at this structure, these two substituents are in different positions relative to the ring. One is below the ring, the other is above the ring. So this is called a trans structure when it comes to the positions of these of two substituents, not necessarily on neighboring carbons. They can be 1 or 2 carbons apart from each other, but if one of them is below, the other is above the ring, we call that a trans type configuration. Okay, on the other hand, in this one, the two substituents are in the same position relative to the ring. They both are above the ring in this specific case, so we call it a cis configuration, where we refer to two substituents on the same position relative to the ring. So they're cis-trans isomers. In general, it is called configurational isomers because they are the same structure. They're not structural isomers because the atoms all have same connectivity, but steric-wise, if you look at sterically, they're not the same configuration. There are two different configurations, and in this specific case, it's cis-trans. Those are cis-trans isomers. The other way to look at it is that they're not conformers. They might look like conformers, but they're not, because to be a conformer, let's say for this structure to be a conformer of this one, then all the E bonds in this structure would be turned into A bonds in this structure. That's the only way they can be conformers of each other. But in fact, this method, which is in E bond, still exists in E bond in this one. So they're not, because of that, they're simply not conformers. It's as simple as that. Okay, so they're not structural isomers, not conformers, not identical, of course, but cis-trans. Let's look at it like this. Draw them into a simpler plane type structure. So here we have bromine below the ring, right? And methyl group above the ring. Whereas here we have both of them above the ring. So this makes it maybe easier to see that there's cis-trans isomers. Alright, so on to the next part. Okay, this pair of structures to me are also cis-trans isomers, just like the last one we did, because in this structure the two chlorine substituents are on one side of the ring. They're both below the ring, whereas in this one is above and one is below. They're on opposite sides of the ring. So this is the trans isomer. This is the cis isomer. So the two of them are cis-trans isomers. Okay, and I don't think we need to draw the planar ring structure to see this time. I'm sure it's pretty obvious to you by now. Also, again, the other way to look at it is that they're not conformers, because to make this one a conformer of this one, the bonds will have to all change. Here we have two E bonds, E bond and E bond. If we had a conformer in a conformer relative to this one, these two would be turned into both A bonds, two A bonds in a conformer, whereas here we have one A and one E. So this is not a conformer. It is a configurational isomer, specifically a cis-trans isomer. You're never going to make this structure by simply trying to draw a different conformer of this one. Okay, that's because by rotating carbon-carbon single bonds, it's never possible to turn this one into this one. That's why they are not conformers to each other. Okay, so alright, next on to the last one, the question. Okay, last pair of today's question. This pair actually seems to me to be a pair of conformers. Conformers this time, or conformational isomers, because if you look at those two, they're the exact chair conformations that you would draw for this compound. If I were asked to draw the two chair conformations out of this same structure, these would be what I would come up with. Okay, so in other words, a pair of chair conformations from the same compound would always be a pair of conformers or conformational isomers. So, and they're not identical. They're not identical because one has the E bond for the chlorine substituent and the other has A bond. And we know that identical structures are supposed to have same type bonds for the same given substituent. So they're not identical. And they're not structural isomers because they do have the same connectivity for the different atoms to each other. The atoms are connected in the same order for this structure and for this structure too. So they're not cis-trans isomers either, because for one thing, we have only one substituent for each ring. There's no such thing as cis-trans configuration, cis-trans configurations. Sorry. So, and also cis-trans configuration or configurational isomers cannot be obtained by giving thermal energy to one isomer. By applying enough thermal energy to a given structure, you are only able to convert it into a conformational isomer, back and forth. You're not going to be able to turn a structure into a structural isomer or configurational isomer simply by giving it thermal energy or by rotation of the carbon-carbon single bonds. That's not going to change the structure or the configuration. It's only going to change the conformation. That's also why these two are conformers, because they are interconvertible to each other by thermal means. And again, there are a pair of chair conformations for the same compound. So again, they're a pair of conformational isomers. And that's that. Thank you so much for watching. Please do not forget to subscribe to our channel or visit my website at MacroLearning.com. Again, thank you so much for watching. Hope you enjoyed it, and see you next time. Bye.